room. And the second you step through the doorway, a silent, invisible laser immediately locks onto the back of your phone.
Like a sci-fi movie.
Literally.
Yeah.
It tracks your every step just to feed you a continuous stream of gigabit data. You never share a frequency with the person standing next to you.
Right.
You never experience a drop in bandwidth. The network physically maps your location in three-dimensional space and hands you a completely personalized connection.
It's pretty mind-bending stuff.
It really is. So welcome to today's deep dive. I'm your host, and I'm joined by our resident tech expert. We are thrilled you're joining us today.
Hey, everyone. Glad to be here.
Because our mission today is to tear apart a single, incredibly dense piece of source material. We got our hands on a short, almost deceptively simple technological overview from a company called AI Atlas.
Yeah, and they're teasing a brand new network technology they call NI6GNET.
Right. And while the source is brief, it is just packed with these sci-fi level claims about the future of internet connectivity.
The document is literally a handful of sentences, but it outlines a fundamental rewriting of network architecture.
Completely.
We are moving away from the concept of bathing an entire room in radio frequencies, which is, how we've handled wireless communication for decades.
Yeah.
And we're moving toward this hyper-targeted, free space optical delivery.
Okay, let's unpack this. The very first claim AI Atlas makes in this text is about the physical hardware responsible for delivering that connection.
Mm-hmm.
They state that for NI6GNET, quote, one compact head forms up to 100 fiber-grade light beams.
Yeah.
Then they add this really crucial mechanical detail. They say no cables, no moving parts.
Which is huge. What's fascinating here is the absolute engineering necessity of that no moving parts constraint.
Right, because I'm picturing like a high-tech disco ball. Or
Yeah.
a concert spotlight constantly swiveling around, right?
Yeah, exactly. In the world of optics, if you want to point a laser at a moving target, the traditional method involves physical gimbals.
Like little motors?
Right. You use tiny motorized mirrors to mechanically steer the light.
Wait, how does a single compact head shoot up to 100 distinct beams without any moving parts to aim them? Mechanical parts are the enemy of scale, right?
Oh, absolutely. Motors burn out, gears strip, physical friction introduces wear and tear.
If you have a single compact head trying to physically swivel 100 different lasers to track 100 different people moving randomly around a room.
The latency alone would be catastrophic.
Right. Not to mention the hardware would probably just shake itself to pieces.
Exactly, which means this system has to be completely solid state. They are achieving beam steering either electronically or optically, likely utilizing something called optical phased arrays.
Okay, optical phased arrays.
Yeah. Instead of physically tilting a mirror to point the light, you manipulate the light waves themselves to change their direction of travel.
Let me test an analogy here for how that phased array steering actually works in practice, just to make sure we're, visualizing the physics correctly.
Okay, go for it.
Imagine a row of 10 synchronized swimmers sitting on the edge of a calm pool.
Okay.
Legs dangling in the water. If all 10 swimmers kick forward at the exact same millisecond, they create a single straight wave that travels directly across the pool.
Right, they reinforce each other.
But if they stagger their kicks, say the swimmer on the far left kicks first, then a microsecond later the next swimmer kicks, cascading down the line.
I see where you're going with this.
That wave they generate doesn't go straight anymore, does it? The interference pattern causes the combined wave to travel away from the wall at an angle.
That is a brilliant way to visualize it. You are describing the manipulation of the wave's phase.
Okay.
By independently controlling the phase of the emission across a flat microscopic array, you cause the light waves to constructively interfere in a specific direction.
And destructively interfere in all other directions, right?
Exactly. The beam bends and aims itself purely through the physics of interference, without a single motor turning.
And because it's solid state, the speed at which you can change that kick timing in our analogy, is effectively instantaneous.
Oh, yeah. You can redirect that beam of light millions of times a second. You can steer it, split it, and constantly adjust its trajectory with zero mechanical lag.
That is wild.
It really is. And that brings us to the other critical phrase in their claim, fiber-grade light beams.
Right.
By operating in the optical or near-infrared spectrum rather than the radio frequency spectrum, the bandwidth capacity just explodes.
So you are essentially taking the data capacity of those physical fiber optic cables buried under our streets and just launching it through the open air.
Precisely, which fundamentally changes the hardware footprint for the end user.
So for you listening right now, picture the current tangled mess of home router cables required to get high-speed internet into your devices.
That's a lot of infrastructure.
Right. You have an optical fiber running under your street, terminating at a heavy plastic router in your living room, which then blasts RF signals through your drywall.
And AI Atlas is proposing a scenario where a silent, motionless array, maybe embedded in a ceiling tile or streetlight, simply shoots the data straight to your device's receiver.
Wow. It just replaces all that static physical infrastructure with dynamic, frictionless delivery.
Yeah, the bottleneck of the home router is bypassed entirely.
Okay, here's where it gets really interesting. We know what the tech is, right?
Yeah.
Solid-state optical phased arrays. But the source material makes a massive claim about how it interacts with the user. The text states, quote, "Every user gets its own beam, and when a user moves, the beam follows automatically."
Yeah.
They literally brand it as wireless fiber that finds you and follows you. It's like a personal digital shadow or a sci-fi tractor beam.
That is the shift from frequency division to spatial division.
Let's drill into that because I want to look at the logistics of this multi-user tracking. If every single user gets their own dedicated beam that follows them, what happens in a crowded room? Does the system get confused?
Well, the source specifies that a single head forms up to 100 beams, right?
Right.
So they are explicitly designing this for multi-user, high-density environments.
But light requires line of sight. If I'm sitting in an airport terminal and 100 people are walking past me, dragging luggage, crossing in front of my device, doesn't my beam just get constantly blocked?
If we connect this to the bigger picture, we have to look at how this fundamentally redefines the concept of a Wi-Fi zone.
Okay, how so?
Well, you're absolutely correct that free space optics suffer from occlusion. A physical body blocking the light stops the data.
Right.
So to maintain a persistent connection, the network cannot rely on a single linear beam from one ceiling node. It's no longer a shared pool of invisible radio waves that gets weaker as you walk away.
So it has to have redundancy. The network actually has to map the room.
Exactly. The entire environment becomes a mesh. If an optical node on the ceiling detects that your primary beam is about to be occluded by a passing person,
It switches.
yes, the solid-state nature of the phased array means it can instantly bounce a beam off a reflective surface to reach you. Or it instantly hands off your connection to a different compact head mounted on the opposite wall. And that handoff happens in nanoseconds.
So you, the user, never experience a drop in packets.
Never.
But that requires an astronomical amount of real-time spatial calculation. The network isn't just sending you data. It is continuously calculating the three-dimensional geometry of every moving object in the room.
Yep. Just to predict and route around physical obstructions. It is essentially creating a high-resolution, real-time topographical map of the physical space.
All just to maintain the connection.
Contrast that with our current RF infrastructure. When you connect to Wi-Fi at a crowded airport, you are fighting for a slice of shared spectrum.
And I always use the loudspeaker analogy for that. Everyone is trying to listen to the same speaker
Right.
in a crowded room.
Right.
And the more people yelling back at it, the worse the bandwidth gets for everyone.
Exactly. The signal degrades due to congestion, interference from neighboring networks, and physical distance from the router.
But with NI6GNET's spatial targeting, your bandwidth is entirely isolated.
The array is whispering directly to your device via a dedicated optical link.
It's like VIP internet.
It really is. The person sitting 2 feet to your left has their own dedicated link. Your data streams never intersect in the spectrum.
Meaning the concept of network congestion effectively ceases to exist. The network molds its physical delivery to your exact location in space.
Right.
But that leads to the next logical hurdle in this architecture.
The backhaul.
Yeah, if we have these compact heads mounted all over an airport or a corporate campus, tracking thousands of users with pinpoint laser accuracy, where do the heads get their internet connection from? The source material gives a very specific, I would say highly unconventional answer. It says, quote, "Backhaul comes by LEO satellite, aerostat, or drone."
This raises an important question about the specific backhaul methods they listed.
I mean, an aerostat, like a blimp or balloon. And drones. It's basically a flying internet relay station.
Yeah, LEO satellites, aerostats, and drones all share one thing in common.
They aren't on the ground.
Exactly. They don't rely on ground-based infrastructure. The backhaul is the spine of the network, right? It connects the local distribution node back to the global data centers.
And traditionally, that spine is buried in the dirt. It's the massive undersea cables and terrestrial fiber networks.
But going airborne means decoupling from the terrestrial grid entirely.
But why go through the trouble of beaming internet down from a drone or a balloon instead of just plugging this compact head into a wall?
Well, decoupling is the key operational advantage. If you rely on terrestrial fiber for your backhaul, your network deployment is inherently constrained by construction, permitting, and physical geography.
Oh, sure. Trenching fiber is slow and incredibly expensive. You can't just lay fiber across a mountain range in an afternoon.
Right. But you can launch a drone from the back of a truck in 5 minutes, or position a high-altitude aerostat over a valley in a few hours.
So this isn't just about giving my apartment a slightly faster connection.
No, this is about dropping a high-capacity, fiber-grade network into environments where the internet simply does not exist, or where it has been catastrophically compromised.
Like disaster zones.
Exactly. Consider disaster recovery. If a tsunami takes out the coastal fiber infrastructure and the cell towers, emergency operations are crippled.
Yeah, communication goes dark.
But with a system like NI6GNET, responders could deploy a series of compact heads on tripods around a command center.
And those heads use optical tracking to connect back up to a hovering drone.
Yes, which in turn relays the signal via laser link to a LEO satellite constellation.
Wow. You've just established a pop-up, gigabit-speed, multi-user tracking network in the middle of a disaster zone, completely independent of the local power grid or physical cables.
And because the drone-to-satellite link is also likely optical, free space lasers communicating in a vacuum, the latency might actually be lower than routing the data through glass fiber cables on the ground.
Wait, really? Lower latency than physical fiber?
Yeah. Light travels faster through the vacuum of space and the thin upper atmosphere than it does bouncing through the core of a glass fiber optic cable.
Oh, that makes sense.
When you bypass the terrestrial routing hops and beam data directly between ELO satellites and aerial relays, you shave milliseconds off the round trip.
Which is massive for algorithmic trading, remote robotics, things like that. It also opens up deep-sea maritime operations, right?
Oh, absolutely. Moving ships, right?
A cargo ship in the middle of the Pacific could have a compact head mounted on the mast, communicating with the LEO satellite, feeding 100 solid-state tracking beams down to the crew.
It physically severs the invisible loosh tying our data to the Earth's crust. It creates a completely off-grid internet backbone.
Incredible. So what does this all mean for the listener right now?
Well,
We've established the tech, the user experience, the sky-based infrastructure. The final logical step is to ask, is this real? And how do we get it?
yeah, the commercial reality.
Exactly. The text ends with a very specific call to action. It says, from AI Atlas, reserve your pilot at aatlasings.ca. So does this mean average consumers can just go buy this tomorrow?
The terminology there, reserving a pilot, signals exactly where this technology currently sits. This is not a consumer product.
So I'm not going to Best Buy to pick up a NI6GNET compact head to replace my Wi-Fi router this weekend.
No, definitely not. Directing users to aatlasing.ca to reserve a pilot indicates the tech is in an early deployment or testing phase.
Okay, so who are the pilots for?
They are typically aimed at enterprise, industrial, or municipal early adopters. AI Atlas is looking for partners to validate the system at scale.
Because testing a system designed to optically track 100 simultaneous targets requires an environment that actually pushes those limits, right? A single user in a living room doesn't exactly stress test the spatial mapping algorithms.
Exactly. They will be looking to partner with heavy industry. Think of an automated million-square-foot logistics warehouse. You have hundreds of autonomous guided vehicles, AGVs, zipping around, moving inventory. If those robots run on traditional Wi-Fi, they suffer from packet collisions and dead zones.
And a dropped signal means a robot stops moving, which cascades into massive logistical delays.
But if you outfit that warehouse with these compact heads, every single robot gets its own dedicated optical link.
The network mathematically tracks their physical coordinates, guaranteeing uninterrupted data to every machine.
Right. Or consider a smart manufacturing facility where robotic arms require ultra-low latency data to perform precision assembly.
So it will likely show up in corporate campuses or city infrastructure first. The pilot phase targets environments where reliable, unshared bandwidth translates directly into millions of dollars in efficiency.
And once those industries fund the optimization of this hardware, the cost curve starts to drop.
That makes sense.
That is when we will start seeing it bleed into public infrastructure.
Okay, let's do a quick recap of the massive ground we just covered from those few sentences in the source material.
We covered a lot.
We did. We started by looking at replacing cables with 100 invisible light beams, utilizing solid-state optical phased arrays to steer light without a single moving part. Then we examined the multi-user tracking, exploring how the network physically tracks your movements to deliver dedicated, unshared bandwidth.
Right.
And finally, we looked at how all of this is powered by a backbone of satellites, drones, and aerostats, completely off the terrestrial grid.
The underlying theme here is the elimination of friction.
I want you, the listener, to hold on to that core premise. Imagine never hunting for a signal again, because your own dedicated beam of wireless fiber is quite literally looking for you. The infrastructure is actively hunting your device to feed you the data you need.
It promises unparalleled convenience. But, as we transition from a world of invisible radio waves to a world of hyper-precise optical tracking, I think there is a profound, lingering question we have to consider.
Oh, let's hear it.
If we are moving toward a future where our internet connection requires a literal beam of light to automatically and precisely track our physical movements,
Right.
whether from a drone hovering in the sky or a compact head mounted across a room, what does that level of hyper-precise physical location tracking mean for our privacy in public spaces?
Oh, wow. That completely flips the perspective.
Right now, a cell tower knows you are generally within a few miles of its radius.
Yeah.
But if the network always knows exactly where you are standing to keep you connected, what else could that data be used for?
We wanted the ultimate frictionless connection, and it looks like we might get it. But the cost of that untethered freedom might be an invisible leash that never, ever takes its eyes off of us.
Something to think about.
Absolutely. Thank you so much for joining us on this deep dive into the architecture of tomorrow. Keep questioning the tech around you, and we'll catch you next time.